Hello everyone, welcome to the second week of CS 110 at VCCS. My name is Amit Brahmbhatt, and today we are going to talk over chapter 2 concepts. So let me go ahead and share the screen. Okay. Here in this lecture, we are going to talk about binary values in number systems. Computers represent all data, numbers, text, images, and sound using number systems. Humans naturally use base 10, but computers only rely on base 2 because electronic circuits can reliably represent only two states, on and off. This chapter explains how numbers are categorized, how positional notations work, and how values can be converted between bases. These ideas are foundational to computing because every piece of information in a computer is ultimately encoded numerically, most often in binary. We begin by distinguishing among different categories of numbers, helping us understand how values are classified in mathematics and computing. Next, we examine positional notation, which explains why the position of a digit determines its value. You will learn how to convert numbers from bases other than 10 into base 10, which is essential for interpretation and verification. We also cover the reverse process, converting base 10 numbers into other bases such as binary, octal, and hexadecimal. In addition, this chapter explains the relationships among base 2, 8, and 16, and why these bases are especially important in computing because computers operate using binary. Understanding base systems that are powers of 2 is essential for understanding how data is stored and processed internally. Numbers 1 of 2, neutral and negative numbers. Neutral and negative. Natural numbers include 0 and all values that can be generated by repeatedly adding 1, such as 0, 32, or 100. These numbers are commonly used for counting and measuring quantities. Negative numbers, on the other hand, are values less than 0 and are represented using minus sign. Examples include negative 24, negative 1, negative 32, etc. Negative numbers allow us to represent concepts such as debt, temperatures below freezing, or movement in the opposite direction. Understanding this type of numbers is important because they form bases of integers which are widely used in programming and computing operations. Now, integers include all natural numbers, their negative counterparts, and 0. This set allows us to represent quantities both above and below 0 without using fractions. Rational numbers go to a step further by including any number that can be expressed as quotient of two integers, such as 3/7 or negative 2/5. Rational numbers are important because they allow computers to work with proportions and ratios. However, many rational numbers cannot be represented exactly in binary, which leads to approximation and rounding computing calculations. Recognizing the differences between these numbers helps explain why some values are stored precisely while others are only approximated. Positive notation. How many ones are there in number 642? The answer depends entirely on the base of the number system being used. In base 10, 642 represents 600, 4 tens, and 2 ones. But if we change the base, those same digit numbers can represent something very different. This illustrates a key idea. Digits alone do not define a number's value. Instead, the base of the number system determines how each digit contributes to the total. Positional notation is critical in computing because it explains how both human readable decimal and numbers and machine readable binary numbers are structured. Base determination determines the meaning. So, the base of the number system determines both number of the symbols available and the value of each digit's position. In base 10, each position represents power of 10. In other bases, positional values change accordingly. This concept is central to understanding how numbers are represented across different systems. Without positional notation, efficient numeric representation would be impossible. This idea explains why computers, which use binary, interpret numbers differently than humans, who typically interpret numbers in base 10. Continuing with our example, the 6 represents 6 times 10 squared, the 4 represents 4 times 10 to the first power, and the 2 represents 2 times 10 to the 0 power. The exponent tells us the position of the digit and its corresponding weight. This positional weighting system allows us numbers to be compactly represented. The same principle applies in any base. Each digit's value is determined by the base raised to a specific power. Understanding this concept is essential for converting numbers between bases and for understanding how computers evaluate numeric values internally. Each digit in a number is multiplied by the base raised to a power that corresponds to digit's position. The almost rightmost digit is multiplied by the base raised by the 0, and each position to the left increases increases the exponent by 1. In the formula, the base determines the numeric system. The number of digits defines how many terms are used, and each digit contributes to its weighted value to the total. This generalized approach allows us to analyze numbers in any base using the same method. The formula formalizes what we intuitively do when reading the numbers in base 10. Now, what if that number has a base of 13? Although digits look the same, their meaning change because the base has changed. The number 642 in base 13 is converted by multiplying each digit by powers of 13 rather than 10. When the values are added together, the result is 1068 in base 10. This example reinforces the idea that numerals value depends on its base, not just its digits. It also highlights why base conversions are necessary in computing, where internal binary values most often be interpreted and displayed in decimal form for human understanding. The decimal is a base 10 and has 10-digit symbols, 0 to 9, and binary has a base 2 and a 2-digit symbols, 0 and 1. The simplicity is ideally suited for computers because electronic components can reliably distinguish between the two states, such as low voltage and high voltage. Every number stored in a computer is ultimately represented using combinations of zeros and ones. While binary numbers may appear unfamiliar at first, they follow the same positional notation rules as decimal numbers. Understanding binary is essential for understanding how computers store data, perform calculation, and manage memory. Valid digit in bases. A number can only contain digits that are valid for its base. In any base n system, the allowed digits range from 0 up to but not including the base itself. For example, base 10 allows digits 0 through 9, while base 2 allows only 0 and 1. The slide invites us to examine numbers like 122, 198, 178, or G1A4 and determine which bases they could belong to. Based on the symbols, for instance, a letter such as G cannot appear in decimal or octal but might be valid in a higher base. This rule is essential in computing because incorrect digit usage can immediately signal invalid data or representation errors when working with different number systems. Base is higher than 10. When we exceed the base 10, we need two additional symbols to represent values beyond 9. The most common example is base 16, also known as hexadecimal. Hexadecimal uses digits 0 through 9 and then letters A through F, where A represents 10, B represents 11, and so on up to F, which represents 15. Hexadecimal is widely used in computing because it maps cleanly to binary. Every hexadecimal digit corresponds exactly to 4 binary bits. This makes binary values easier for humans to read and write while preserving the computer's internal representation. Converting octal to decimal. So the example shown here, the octal number is 642. To convert it, each digit is multiplied by power of 8 corresponding to its position. The 6 is multiplied by 8 squared. The 4 is multiplied by 8 to the power first power and 2 by 8 to the 0 power. Adding these values together yields decimal equivalent of 418. This process highlights how positional notation works consistently across all bases. By converting octal to decimal, we move forward from a computer-friendly representation towards a human-friendly one, which is useful for debugging, system configuration, and understanding stored values. Converting hexadecimal to decimal. DEF is what is going to be converted. So we can see D is being multiplied by 16 to the power 2, then added to E multiplied by 16 to the power 1 and F to the 16 to the power 0. And that gives us 3,567 in base 10. So in base 16, after 9, 0 to 9, after 9, we say A, B, C, D, E, F to represent the following digits. Now, here is an example of converting a binary number to a base 10. In the same fashion, we count how many digits it is. So it's 7 digits number. So we start with multiplying the first number with 2 to the power 6. Then next digit to multiply 2 to the power 5, all the way to the last digit 0 multiplied 2 to the power 0, which gives you 0. And then adding them all up gives you 110 in base 10. Here's an example for arithmetic in binary. Focusing on addition, we can see how addition works in binary because binary has only two digits, 0 and 1. The rules of addition are slightly different from decimal. The key idea is that the 1 plus 1 equals 0 with a carry of 1. The slide shows how carries propagate across multiple positions during addition. This process mirrors decimal arithmetic but uses base 2 instead of base 10. Binary arithmetic underlies every operation performed by a computer's processor, from basic calculation to complex algorithms. Understanding binary addition provides insights into how processors perform arithmetic at a hardware level. Now, here is an example for subtraction. And this reminds us the concept of borrowing. Just like in decimal subtraction, borrowing occurs when subtracting a larger digit from a smaller one. In binary, borrowing means taking one from the next higher bit, which represents a value of 2 in the current position. The example illustrates how subtracting binary number requires careful tracking of borrowed bits. Binary subtraction is essential for arithmetic logic unit in processors and is fundamental to operations such as comparison, subtraction, and memory address calculations. Counting in power of two bases. So here they are just showing us how in the slide represents the binary from 0 to 10 in decimal and how the same numbers would be represented in octal as well. And this is something that should come in handy in many simple exercises for any course that uses the binary representation. The bases have special relationship that makes counting and conversion straightforward. Binary counts in power of 2, octal in powers of 8, and hexadecimal in power of 16. Understanding these patterns helps us explain why octal and hexadecimal are useful shorthand representation of binary values. This slide visually reinforces how numbers progress in different bases and why certain bases align particularly well with computer hardware. Converting binary to octal. Here is an example that shows how to convert a binary number to octal by grouping bits. Starting from the right, binary digits are grouped into sets of 3. Each group is converted into its local equivalent. For example, the number 10101011 is grouped and converted into the octal number 253. This technique works because each octal digit corresponds exactly to 3 binary bits. The method is much faster than converting first to decimal and is commonly used when working with low-level system values and permissions. So basically, when we look at these groups, 0, 1, 1, 1, 0, 1, we can look at the previous slide and find out what 0, 1, 1 is and 1, 0, 1 is, which is 3 and 5. So you can see 0, 1, 1 is 3, 1, 0, 1 is 5, and 0, 1, 0 is 2. And that gives us the 253 in base 8. Now moving forward, converting binary to hexadecimal by grouping bits into sets of 4 starting from the right. Each group of 4 bits maps directly to a hexadecimal digit. The example converts binary number 10101011 into hexadecimal AB. This process takes advantage of the one-to-one relationship between 4 bits and one hexadecimal digit. Converting binary to hexadecimal is extremely common in computing because it provides a compact, human-readable way to express long binary sequences while preserving exact values. Abacus. One of the oldest known computing tools, the abacus uses rows of beads to represent numerical values and perform arithmetic operations such as addition and subtractions. Each bead's position corresponds to a numeric value, making the abacus an early example of positional notation in action. Although simple, the abacus embodies concepts still used in modern computing, including structured representation and systematic calculation. The abacus shows that while today's computers are electronic and extremely fast, the fundamental idea of representation of numbers physically or symbolically has existed for thousands of years. Understanding historical tools like abacus helps us appreciate how modern computation evolved from mechanical aids. Converting decimal to other bases. Here is an algorithm for converting a number in base 10 to other bases. While the quotient is not zero, it's a loop. And basically you loop and you say divide the decimal number by the new base, then make the remainder the next digit to the left in the answer, replace the decimal number with the quotient, and keep on looping in that. And that algorithm pretty much helps you convert the number base number 10 to other bases. Mastering this method enables programmers to interpret stored values, debug low-level code, and confidently move between representations. Converting decimal to octal. So what's a 1988 base 10 in base 8? The conversion process would start by dividing the decimal number by 8 and re, recording the remainder. The quotient is then divided again by 8, and the process continues until the quotient becomes 0. Each remainder represents a digit in the octal number. This step-by-step procedure emphasizes how conversion algorithm works mechanically. Seeing the full working reinforces that number conversion is not guesswork. It follows predictable, repeatable process. Understanding this process is important because base conversions are a common task in systems programming and digit logic. Converting decimal to octal. This slide completes the conversion of 1988 from decimal to octal. After performing the repeated division by 8 and collecting the remainders, the final octal representation is obtained by reading the remainders in reverse order. In this example, the result is 3704 in base 8. This slide demonstrates how the algorithm consistently produces accurate results when following correctly. Practicing these conversions builds confidence and reinforces an intuitive understanding of how different number systems relate to one another, especially those used internally by computers. Converting decimal to hexadecimal, 102. So what's 3567 base 10 in base 16? Again, I've used the same algorithm, repeated division method, but the division is performed using base 16. As quotient and remainders are produced, any remainder greater than 9 is represented using letters A through F. This example shows how hexadecimal uses alphabetical symbols to efficiently represent larger values. Hexadecimal is widely used in computing because it is compact and maps directly onto binary data, making it easier for humans to interpret machine information. Here we see how we actually do it. Basically, we follow the same division process and translate the remainders into hexadecimal symbols, yielding the final result, DEF. This example reinforces both mechanical nature of base conversion and the usefulness of hexadecimal representation. The clean mapping from binary to hexadecimal makes hexadecimal an ideal format for memory addresses, color codes, and debugging output. Understanding this slide helps bridge gap between human readable numbers and machine level representations. Binary numbers and computers. Now this slide explains how binary numbers are physically represented in computers. Computer stores data using binary digits or bits where each bit corresponds to an electrical state such as low voltage or high voltage. The states are interpreted as 0 and 1, regardless of how high level information appears to users. All data inside a computer, text, images, audio, and video, is represented using combinations of bits. This slide emphasizes that binary is not just mathematical concept, but a physical reality of how computer hardware operates. Binary and computers, bits, bytes, and words. This slide introduces key storage units used in computing. A byte consists of 8 bits and is the basic unit of storage in most computer systems. A word is a larger group of bits processed as a unit by a computer's processor. The number of bits in a word, called the word length, determines how much data the processor can handle at once. Common systems include 32-bit and 64-bit architectures. Word length affects performance, memory addressing, and size of numbers that can be processed efficiently. Binary and computers. Here's a visual representation of how bits are organized and processed. The image reinforces how binary data moves through hardware components such as processors and memory units. And here is an example of an early prototype of an IBM machine. Ethical issues, the FISA code. Ethical issues related to computing and surveillance. The Foreign Intelligence Surveillance Code, FISA code, oversees government requests for surveillance related to national security. Many people become aware of FISA code through public disclosures about electronic surveillance programs. The slide encourages discussion of oversight, transparency, and checks and balances between government and entities. It also raises questions about balance between national security and individual privacy. These ethical considerations are increasingly important as computing technology enables large-scale data collection and analysis. Grace Murray Hopper. This slide highlights Grace Murray Hopper, a pioneering computer scientist and naval officer. Hopper played a key role in the development of early programming languages and was instrumental in the creation of COBOL, one of the first high-level programming languages. She also popularized the idea of machine-independent programming languages. Hopper's work helped make computers more accessible and programming more efficient. Her legacy continues to influence modern software development. She is remembered as one of the most important figures in the history of computing. Now, we close the chapter with reflective questions that connect key concepts. It asks about concepts that makes positional notations possible, encouraging recall of base systems and place values. The question about preschool classification sets emphasize early numerical reasoning. The slide also revisits abacus and introduces biquinary system, which combine 2 and 5 based counting methods. These questions encourage students to think beyond formulas and connect number systems to both historical tools and modern computing concepts. So here was your chapter 2. I hope you learned a lot. I'm looking forward to see you in the class or in one of the engagement sessions and hear from you via emails if you have any questions. Take care, everyone.